Okay, so here we have a metric space XD and we have two compact subsets A and B. Our target is to show that the union A union B is also compact. Okay, so the situation is here we have a metric space X comma D and we have two sets A and B. Alright, so each of them are compact. Now our target is to show when we take their union that is also compact. Alright, so let A and B be compact subsets of metric space X comma D. Okay, so we have two compact set of a metric space. Now we want to show, the target is to show that A union B is compact. Alright, so we know the definition for proving compact. We take a open cover and we want to show that every open cover will have a finite subcover. So let's take a general open cover. So let G, which is equal to G lambda, such that lambda belongs to some indexing set I, be an open cover for A union B. Okay, that means A union B is covered by all the unions G lambda, where lambda belongs to the indexing set. Alright, so the next target is to find a finite subcover for this. So how are we going to use that? So we will use the find compactness of A and B, right? So right now we know that A union B is covered by some sets like this, and we want to cover a finite. We want to find a finite balls which can cover A union B. So we will divide this problem into two parts. In one part we find the finite subcover for A, in the other part we find the finite subcover for B, and they together will form the finite subcover for A union B. That is the idea. Okay, so from this implies A is also contained in A union B, and that is contained in G lambda, where lambda belongs to I. That means G is also open cover, also an open cover for A, right? Because A is covered by their unions, and we know whenever such thing happens, G also becomes an open cover for A. But we know, but A is compact, so therefore by definition G has a finite subcover for A, right? That means there exists some G alpha 1, G alpha 2 up to G alpha n1 such that I can cover A by, so they are all in G such that A is covered by union G alpha I from 1 to 1 to n1. Okay, that means the set A, the set A which we had, that is covered by n1 balls, that is something like this. So from the open cover G there are n1 elements which can cover A. So same logic we will apply for B also. So also B is contained in A union B, and that is contained in union G lambda, where lambda is in I. So again that would imply that G is an open cover for B. But again it is given that B is compact. So but B is compact, so that would imply there exists some G beta 1, G beta 2, and like that finite set, that is G beta n2 belonging to G. These elements are coming from G, such that B can be covered by their unions. Okay, so G beta I from 1 to n2. Alright, so we had a finite subcover for A, we had a finite subcover for B, Now taking their union, so take union of 1 and 2. So what we will get, A union B is covered by union G alpha I from 1 to n1, union G beta I from 1 to n2. That means there are total n1 plus n2 elements that can cover A union B. So therefore this is a finite subcover given by G. That means G has a finite subcover for A union B, and this is like any random G we had taken. So this is true for any open cover. This implies A union B is compact. Okay, so we have just made the use of compactness of A and B, and that helps us to pull out finite subcover for A, finite subcover for B, and they together form a finite subcover for A union B. Okay, thank you.